In this op-amp example, we're looking for the output voltage versus the input voltage as it goes through the op-amp and 3 resistors with resistances R1 and R2. And then we have a second resistor also with resistance R1. And we want to know, is this a inverting or non-inverting circuit? Everything is going to start at equilibrium. Everything is going to start with initial condition 0. We're saying that there's no voltage for a long time. Everything is discharged. Then we are going to apply our input voltage. So we're looking to find here what I will call G equals E out over E I. And we'll make a new version of this diagram. It's going to look basically the same, but it's one that we're going to be able to mark up. So I'll copy it down as best I can. I have this EI come up here, adding nodes as I go. Resistance R2, capacitor, and it's grounded down here. And I'll put in the op amp. All right, we have this R1 and R2. They, in this case, though, are not in parallel because you'll see they on one side start at that same node, but they end up at different nodes. So we're not going to be able to simplify that using like an impedance block. In this case, I'm going to keep them separate. Okay, so I've copied down the diagram that we're going to be able to add some extra information to, because in this type of problem with the op amps, I like to use the nodal voltage drops. So I like to mark all of the voltages at all the nodes and then start putting in the currents. All right, so I'll start with the easy ones. Because I have a ground here, I know that that node directly touching it is going to have a voltage of 0. And any node that is directly wired to it will also have a voltage of 0. So those 3 nodes, I'm going to copy that those are all 0. They're directly attached to the ground. Now I can also mark here, up here, this has to be EO, because I know that the voltage drop from that top node to the bottom node is EO, and at the bottom it's 0. So it must be EO at the top. Same idea here for EI. This node must have a voltage of EI, since there's a voltage drop of EI before I get to 0. So it has to be EI, since EI minus 0 will give me that EI. And I really just can copy this here, and I can copy this here, since those are just wired together. All right, so I'm left with 2 nodes whose voltage I don't know at the moment. But there is some information I do know, because both of those nodes are attached into the op amp. And with an ideal op amp, we are saying that the voltage at the positive input and the negative input must be equal. I don't know what that voltage is as a number right now, because there's a capacitor between it and 0 for that bottom node going into the positive terminal, and there's a resistor between it and EI. So I don't know, I can't say it's 0, I can't say it's EI, but what I could say is it's some unknown value right now, I'll call EA. And because the other input has to have the same voltage, it must also be true that the voltage at that node is EA. So I don't know what it is, but that's okay. I can just call it a variable for now and use it as I go forward. All right, now I can start looking at currents. I'll just start at this EI terminal and say there's some current here, I. I'm actually not going to use it, but I'll label it at least. And then I get to the next node where I have EI, and then that current is going to split. Currents split when I have these branches. I'm going to say that on the top branch, it's going to be I1, and it'll split on the bottom branch as I2. And using KCL, I know that I1 plus I2 must equal I, because I can't save current at a node. So that I splits into an I1 branch and an I2 branch. Now I'll follow the top branch as I go. So I go across R1 and I arrive at EA. So there's going to be a current split there as well. So it's I1 coming in. I know that for an ideal op amp, the current into the inputs has to be 0. So that is going to have a current of 0. So again, by KCL, this must be I1 because it's I1 coming in. It's I1, or it's 0 plus I1 or I1 going out. So that is preserved. And same idea, if I take that bottom branch, it's I2 going into that bottom node. There's going to be a split there. But it has to be 0 going into the positive input. Therefore, it must be I2 going down across that capacitor C. And then it's I1 coming over here and I1 there. This is going to, we're not going to necessarily use this information, but it's all labeled. So currents are labeled. I don't know what I1, I2 are. These are going to be potentially outputs in my equations. And EA I added as also a potential output in our equations. They can all vary in time, and therefore they're all going to be functions of frequency of S when I do their Laplace transforms. So every node has its voltage labeled either with a known quantity or a new variable I invented, and branches of wire have their currents labeled. So now I can move on to my equation step and use this diagram to start generating some equations. So ultimately, I need E out and EI, or EO and EI, in equations so that I can get my desired transfer function. I'm going to start by doing, again, these nodal voltage drops. It doesn't really matter where I start. I eventually will need something with EI and E out, but let's go here. I'm going to start by going from this node to this node, so that EI node to that EA node. All right, so equation 1. I'm going to go with the direction of current, so it's going to be the end voltage minus the beginning voltage. So I end at EA minus EI. Right, end point minus start point, and I have a voltage drop then of negative R2 times I2, because I'm going across just one resistor. So let's keep a tally here of outputs and our input. All right, so EI is in here, so I do have an equation with my input, which I need, and I have an output here of EA, which is, again, the voltage at those input nodes into the op amp. I don't need to know it, but I have it here. And current I2, which is here, and I'll be able to solve for it. So definitely need more equations, as I have only one equation and two outputs, and neither output is the one I ultimately need, that EO. All right, so I need definitely an equation that has EO in it, so let me do another nodal voltage drop. I'm going to use this EA here as the start point and end at this E out, and I'm going to follow that current through R1, which is I1. So this will be E out minus EA equals, and then the voltage drop here will be the resistance R1 times I1. So I've added here E out as an output and I1 as an output. So I now have four outputs, although again one of them is one I need. So the E out I have, so that's good. The EI I have, that's good. But I'm going to need at least two more equations to get enough equations for all of the outputs I have, if I add no more outputs. Now I'll note that the way I'm doing this is not necessarily the most efficient. This is going to take me, as we see here, at least 4 equations to do. There is probably a more efficient way to go with fewer equations, but as long as we have a solvable system, that's what's going to matter right now. It's not necessarily the most efficient way that we're concerned about as we're going through this material and learning it. All right, so let's see what other voltage drops we can do. And hopefully not add any more unknowns, which really all, if we look at the picture, EI, EO, EA, I1, and I2 are the only unknowns. We have I there, but there's not really much to do with it because it's just going through a plain piece of wire. All right, let me go from this EA down to this node at 0 for another equation. So I'm going with the current I2, so my endpoint 0 minus EA will equal the voltage drop across that capacitor. So it's going to have an impedance of 1 over CS times its current of I2. And if I look, I have not added any new outputs. EA and I2 were already on my list, and C is a constant, a parameter, so it's fine. All right, so I want one more equation here at least so that I can make this solvable system. I am going to go from this EI to this EA. I haven't looked at that branch yet. So I'm going with the current I1. I'm ending at EA, and I'm starting at EI in this one. But it's different than that equation 1 that was going along the bottom branch. Now I'm going along the top branch, so negative R1 times I1 is going to be the voltage drop across that top branch. So looking at my equations, I have 4 equations. I have those 4 outputs, including the one I need, E out, and I have my input EI. So this will be solvable for the transfer function that I'm searching for. So now I will go into Mathematica and put in my 4 equations to get, well, ultimately 4 transfer functions, but the one that I'm concerned with most importantly. And putting these in, EQ1 is going to be EA minus EI, negative R2 I2. My second equation, I have EO minus EA is negative R1 I1. Third equation is 0 minus EA, which would also just be negative EA, but I'll just type the whole thing in, minus, and I have negative 1 over, I'll put a lowercase c here, times S times I2. And the fourth equation is EA minus EI is negative R1 I1. All right, so 4 equations are entered in here, and we just want to verify them for accuracy, and everything here looks like it is put in correctly. So I'm ready to solve it for my 4 outputs. So let's solve EQ1, EQ2, 3, and 4 for EA, I1, I2, and EO. All right, so solving that, everything looks like it solved correctly. It's sometimes easy to make a mistake if maybe I put A capitalized at one place and then lowercase in another, but here everything looks like it was able to solve correctly, and I can reduce this down a little bit. All right, so here are what could become 4 transfer functions for the 4 outputs, but I just am worried about my EO1. So I'm just going to copy this piece and paste it in here. G is E out over EI, so I divide through by the EI by deleting it there. All right, this isn't necessarily in the nicest form yet, so I'm going to now rewrite this using what we usually do. So collect the numerator of G and its denominator. And now we have it in the form we want. So I'm going to take that and we're going to be able to rewrite it. Take this, I have my G is E out over EI equals, now from what I have in Mathematica, I have a negative CR2S plus 1, and I have a positive CR2S plus 1. So it actually turned out all the R1s canceled out for this one. R2 and the capacitor are going to determine what this transfer function is. I'm going to rewrite this one a little bit though. I don't like this preceding negative in the numerator, so I'm actually going to pull out a negative sign and rewrite the numerator then as C R2S minus 1 on the top and a C R2S plus 1 on the bottom. So yeah, I didn't change anything. I just really factored out that negative and put it out in front. And that is the way I'm going to prefer to write this transfer function. Now, if we look at it, it definitely looks different than the previous one we saw. I have a negative out in front, but I also have, which we don't normally see, I have a negative sign in the numerator here. So is this an inverting function or a non-inverting function? Well, actually, it depends. Now, there's a negative out in front, which that sometimes can indicate that we have an inverting function. But this one's a little bit different because of the numerator. Depending on the value of C and R2, it's possible that the numerator could be positive or negative. It's not going to be strictly positive like we often see. So this one we can't really classify as inverting or non-inverting because it's really going to depend on the parameters we choose for C and R2, whether it would invert or be non-inverting in our system. So now we can look, how did we get to this transfer function? We have our op-amp circuit, which I copied down and made our diagram. For the op-amps, I'm going to label all of the nodal voltages that I either know because they're ground or because it's an input or an output, or in this case where we had two nodes that we were none of those. It was not a ground, it was not an input or an output, so I had to give it a new name. I called it EA here. And I knew that the voltage going into the negative and positive inputs of an op-amp are going to be equal. So they're both EA. I then proceeded to start to write the currents, which have to be in variable form. I don't know them. So I know that if I just call this I going into this node, that's going to have to split into two currents that add up to I. I1 and I2 is what I called them. They're going to split again at the next node. So for example, here it splits. It has to be 0 going into the negative input because it's an ideal op-amp. So if it's I1 coming in, therefore it must be I1 going through the top branch. Same idea at the bottom node. It's 0 going into the positive input, therefore it must be I2 going down across the capacitor. Using the diagram, I came up with 4 equations using nodal voltages or node-to-node voltage drops. Again, there's other ways that might be more efficient to do this, maybe a voltage divider or some other technique, but by just selecting 4 pairs of nodes and looking at the voltage drop across them, I was able to get these 4 equations for 4 outputs. EA, that voltage that I created the variable for that's going into the op-amp. I1 and I2, the currents that are going through the top and the lower branch after I splits. And then I have E out, which is what I ultimately wanted. So I came up with 4 equations for my 4 outputs, and I had then a solvable system. Put those into Mathematica to come up with my transfer function. So I can write the transfer function like this negative CR2S plus 1. I think it's a little bit cleaner though to factor out that negative. I would rather not have a negative on the leading coefficient in S. So I factored out that negative so I could rewrite the numerator as CR2S minus 1 and then put that negative out in front. And then that is the transfer function that takes me from my input voltage EI to my output voltage EO.